Welcome back to Logic, Language and Information. In this lesson we will identify the class of predicate logic formulas corresponding to Prolog program clauses and goals. At the end of last lesson we framed our quest for a useful fragment of predicate logic with identity for which an algorithm computing logical consequence can be implemented in software and be practically good enough in answering many of the questions put to it. We use Prolog and its software implementations for this purpose. Our first task is to identify which formulas of predicate logic with identity can be handled by basic predicate Prolog. There is an emphasis here on basic. In this short introduction, we will not be using any advanced features of Prolog. In particular, we will not be discussing the extension with the not provable operator for negation. You can see this in the simpler setting of propositional logic in LLI2 section 6.4. We will, however, allow negated identity assertions expressing difference, and we will be reclassifying them as atomic. We will also not be using any of the built-in arithmetic or list manipulation operations, since they correspond to first-order logic with function symbols. Let's recall the way we formally defined the formulas of predicate logic with identity in the core sections 1 and 4 of this course. Atomic formulas are formed by combining an n-place predicate symbol f with n many names, a1, a2, up to an, expressing that the proposition that predicate f holds of the objects named by a1, a2, up to an. Then in section 4, we extended the atomic formulas to include identity assertions. A1 is identical to A2. The class of formulas was then built up using the propositional connectives. In particular, negated identity assertions expressing difference were classified as complex, non-atomic formulas. Variables were introduced solely as a means of quantification, with a variable x substituted for a name a and then bound by either a universal or existential quantifier. In order to describe the class of formulas used in Prolog, in particular the restricted pattern of quantifiers and propositional connectives that will be allowed, we need to slightly revise the way formulas are formed. To begin with, we introduce a new syntactic category called terms. Every name is a term, and every variable is also a term. Next, we introduce another new category called star atoms. These will include all real atomic formulas, but also expand to allow the occurrence of variables as well as names, without a quantifier in sight. Our first type of star atom is formed by combining an n-place predicate symbol f with n many terms, t1, t2 up to tn, expressing that predicate f holds of the objects referred to by t1, t2 up to tn. The class of star atoms also includes identity assertions. T1 is identical to T2, where T1 and T2 are terms, as well as difference assertions. T1 is not identical to T2. In addition to allowing variables without a quantifier in sight, this reclassification of difference assertions as atomic is a departure from what we did in section 4, but it is not a substantive departure. As we shall see, this inclusion of difference assertions will be the only way we include negation directly in Prolog formulas. To make clear the way in which predicate Prolog sits on top of propositional Prolog, we also include as star atoms propositional atomic formulas thought of as zero-place predicates. And this concludes the class of star atoms. Now, it's important to note that because of the presence of variables, star atoms in general are not real formulas and do not express propositions that are either true or false in any model interpreting their predicate and names in them. Now, for a star atom A, let var of A be the set of variables occurring in A, without duplication. A real atomic formula is a star atom A such that var of A is empty. For a concrete example, let P be a 5-place predicate. Then P X, Y, A, X, Z is a star atom and its variables are X, Y and Z, taking A as a name. The class of star formulas is generated from the star atoms by applying just the propositional connectives. For our present purpose, we are only interested in propositional combinations of star atoms. Now, with this preamble, we can now say what a program clause is. Program clauses are also called definite clauses or positive clauses. And they are star formulas of one of two very simple kinds. Program clauses are either conditional star formulas whose antecedent is a conjunction of star atoms and whose consequent is a single star atom, or else it is a single star atom known as a fact. When convenient, we consider all program clauses as conditionals, with facts falling into the special case where the antecedent is a size 0 conjunction that behaves like the always true formula, as in if true then B, which is logically equivalent to just B itself. Now we need to refer to the variables within a program clause C, so var of C is simply obtained by merging or taking the union of all the variable sets for the component star atoms. Now just to be clear, a program clause C is a star formula, not a real formula. The real formula we are interested in is the one you get to by universally quantifying each of the variables in var of C. These are real formulas that are true or false in a model. We've just taken a route through these things called star formulas in order to describe them. A concrete example, if C is the program clause, if RXY and SYZ and PZA, then SXA, then the universal quantification of C is the real formula for all X, for all Y, for all Z, if RXY and SYZ and PZA, then SXA. For any star formula C, if there are no variables in C, then C is already a real formula, and either universal or existential quantification will add nothing, as there are no extra variables to quantify. With all this lead up, we can now clearly state the class of logical consequence problems addressable in basic Prolog. A knowledge base of information is in some subject domain will be represented by a list P of program clauses and called a logic program. This is typically a mix of facts and conditional rules with and without variables, but whatever variables there are will be universally quantified. A goal G is a list of star atoms, and the corresponding goal star formula is the conjunction D of the goal star atoms G1, G2 up to GK. These are sometimes referred to as subgoals. Now these subgoal atoms are potential consequences of our knowledge base. The variables in a goal are understood as existentially quantified. We want to know if there exists a way to simultaneously satisfy each of G1, G2 up to GK. So, finally, the automated reasoning task addressable by Prolog. Determine whether or not a goal G is a logical consequence of a logic program P. Expressed as real formulas of predicate logic with identity, we want to determine whether or not the existential quantification of goal conjunction D is a logical consequence of the universally quantified program clauses in P. Note the quite restrictive propositional combinations of star atoms involving conjunctions and conditionals, but negation is nowhere to be seen. Well, the only hint of negation is in the form of difference assertions. A is not identical to B, which get to be classified as star atoms precisely so we can sneak in this much negation. Because we are working with predicates, names and variables, but not with function symbols, identity and difference are not too complicated in our setting. Now, we will be spending the rest of this lesson coming to a better understanding of the class of real predicate logic formulas corresponding to program clauses and goals. In the next lesson, 6.3, we'll get down to business with Prolog programming. But to keep up interest in case it is flagging, here's a sneak preview. In predicate Prolog, a yes answer to a logical consequence question is indicated by providing an existential witness in the form of a name mapped to each of the variables in the goal formula. When substituted into the list of goal star atoms, this gives a list of real atomic formulas that are logical consequences of the program, P. Prolog implementations give a means to ask if there is more than one set of existential witnesses for the variables in the goal, and this is done using a semicolon key on the keyboard. Because of the way Prolog instantiates variables, it is good practice, indeed recommended, to use different variables in the goal than those used in the logic program. In terms of logical equivalence of formulas, the choice of a bound variable name does not matter, but for the purposes of computing, it does. When the goal conjunction D does not have any variables, so it is a real formula already, Prolog will either answer true, meaning yes, it is a logical consequence, or false, meaning no, or else Prolog gets stuck in a loop and does not return an answer at all. We will see some of the ways this can happen in lesson 6.4. Now, we start by getting a better understanding of formulas that are logically equivalent to a program clause. This is the case when the formula A, if and only if, the universal quantification of C is a tautology where C is a program clause. In predicate logic, it's going to take a bit more work than in propositional logic to show that a formula is logically equivalent to a program clause. In the propositional case, there are now some more detailed examples of reasoning through a sequence of logical equivalences in a revised version of the LLI2 course notes in section 133 at the end of chapter 1. As was the case for propositional logic, it is useful to have handy a list of known tautology biconditionals to call on when reasoning through a sequence of logical equivalences. In the LLI2 course notes, such a list can be found at the end of chapter 2. Now, one of the more useful logical equivalences we use here is called a prenexing law for the exists quantifier in the antecedent of a conditional. Here, the right-hand side of the equivalence is a formula exactly in the shape we are interested in for program clauses. It is the universal quantification of a conditional. The left-hand side of the biconditional is a conditional with an existential quantifier in its antecedent. The equivalence can be read as saying we can pull the quantifier from inner scope to outer scope, but in the process it swaps from being existential to becoming universal. This can be done provided there is no unintended binding of variables to quantifiers by requiring the side condition that the quantified variable x does not occur free in the consequent of the conditional, meaning either no x at all or quantified x. We will only see cases where there is no occurrence at all of the variable in question. Now, you might like to test out your proof tree skills to confirm that this biconditional is indeed a predicate tautology. The dual prenexing law swaps the existential and universal quantifiers. There are prenexing laws for the other propositional connectives as well, allowing a quantifier to be pulled from inner to outer scope. But it is only in the antecedent of a conditional that prenexing involves swapping the flavour of the quantifier between existential and universal. Okay, let's see an example of reasoning through a sequence of logical equivalences. We will use the shown instance of the prenexing law for exists in the antecedent of a conditional. Now, we start with a formula as shown. It says for all x, sxa, or for all y, for all z, either not rxy or not syz or not pza. We will show that this is logically equivalent to a logic program. First step, use De Morgan's law to rewrite the disjunction of negations as a negated conjunction. Next, we are aiming for a conditional, so pull the negation outwards through the quantifiers, in the process flipping them from universal to existential. We can now apply the material conditional equivalence to get a conditional with existential quantifiers in the antecedent. The variables quantified are y and z, and they do not occur at all in the consequent sxa. So we can apply the prenexing law for the y variable and then apply it again for the z variable to end up with a universally quantified program clause form as claimed. Now it's your turn. Assume A and B are names, X, Y, Z and W are variables, R is a two-place predicate and P is a three-place predicate. Which one or more of these formulas is logically equivalent to a program clause or logically equivalent to a conjunction of two program clauses? You might want to note that universal quantifiers distribute over a conjunction, so breaking into a conjunction of two program clauses is quite easy. Okay, how did you go? We will go through the 5 options in turn. It turns out only one of them is not of the required form. The first, formula A, was meant to be easy. It's a straightforward application of De Morgan's law followed by the material conditional equivalence. Next, B, this one we need to break into a conjunction of two program clause formulas. The first, the universal quantification of a fact, and the second, the universal quantification of a conditional whose antecedent is the difference star atom. Now we can still use the logical relationship that difference and identity assertions are negations of one another, even though they both get classed as star atoms. For C, we first apply the prenexing law to pull outward the existential quantifiers in the antecedent, in the process making them universal, and then break into a conjunction of two program clause formulas. Here, using the tautology, A implies B1 and B2, if and only if A implies B1 and A implies B2. And then distributing universal quantifiers over conjunction. For D, this is the only one where the answer is no. A disjunction in the antecedent of a conditional is a no-go. There's nothing to be done here. It's just not a program clause. For the last one, E, we can apply the prenexing law for exists in the antecedent and then what's known as Curry's law, which is the tautology if A then B implies C is equivalent to if A and B then C. Now, if you have any comments or questions, first go to the course notes and then to the discussion boards and we can follow up there. Now, a predicate logic formula is logically equivalent to a logic program if and only if it is logically equivalent to a conjunction of program clause formulas, allowing size 1 conjunctions. As we saw, it can be useful to appeal to distribution of universal quantifiers over conjunction. On the other side of the double turnstile, a formula is logically equivalent to a goal if and only if it is logically equivalent to the existential quantification of a conjunction of star atoms. Here it is important to note that the existential quantifier does not distribute over conjunction. And also remember that a negated universal is equivalent to an existential negation. Now, it's your turn. Which one or more of the following formulas is logically equivalent to a goal? How did you go? We will work through the 5 options in turn. For this exercise, we get 3 yes and 2 no answers. Option A is yes, apply De Morgan's law to the inner core of the formula, and then that not for all not is equivalent to there exists. For B, the answer is no. Apply first the negated conditional equivalence, and the inner core contains a negated star atom that cannot be moved by any means. For C, the answer is yes, and also uses the negated conditional equivalence. For D, it's another case of not for all not being equivalent to there exists. While for E, the answer is no, because after getting the bank of universal quantifiers out the front of the conjunctions, one of the star atoms is negated and that cannot be moved away. Now, if you have any comments or questions, go first to the course notes and then to the discussion boards, and I'll follow up there. Now, Prolog is associated with the horn clause fragment of predicate logic. First, we explain the clause bit. A star formula is called a clause when it is a disjunction of literals, where a literal is a star atom or the negation of a star atom, allowing size 1 disjunctions here. For example, A1 or not A2 or A3 or not A4 is a clause where the AIs are all star atoms. A star formula is called a horn clause exactly when it is logically equivalent to a clause containing at most 1 positive or unnegated literal. So the example shown here is not a horn clause because it has 2 positive literals. With this terminology, a program clause is a horn clause with exactly 1 positive literal, while the negation of a goal is a horn clause with 0 positive literals, which means all negative literals. The formula in option A in the last exercise illustrated this. Now, it is the negation of the goal that is relevant here because Prolog, like the proof tree method, is a refutation approach that starts by supposing the logic program P is true while the goal G is false, and then seeks to derive a contradiction. So in the end, the class of formulas that need to be handled are all universal quantifications of horn clauses. This brings us to the end of this lesson examining the class of formulas of predicate logic with identity that can be handled by Prolog computations of logical consequence. In the next lesson, we will get down to business with Prolog programming. So see you then.